Hello, welcome to Maths with EJD. In this video, I'll be talking about complex functions. I've made series of videos on complex numbers, and it is that time to talk about functions of complex variables, just like under calculus, we talked about functions of real variables, right? So, in our outline, we'll be looking at the introduction, we'll look at the complex functions and their graphs, and of course, we'll reach a conclusion. So, the bulk of the work is on the second outline. So, going to the introduction, right? Complex functions play a crucial role in mathematics, in physics, in engineering, and various other fields. I mean, you can extend that to things to fields like geology, geophysics, meteorology, and all of those other ones. You know, you have a lot of complex functions playing prominent roles here. Okay, so let's talk about complex functions and their graphs, right? Complex functions are functions of a complex variable. They are functions of a complex variable, which map complex numbers to complex numbers. So just like we did in the case of functions of real variables, right? Where we said that, you know, um, f is a function which maps x to y. There it was mapping real to real, but here you're mapping complex to complex. So you have the inputs, which is the independent variable, and you have the output, which is the dependent variable. So complex functions are functions of a complex variable which map complex numbers to complex numbers. All right. So, um, of course, a very good example would be something like, say, you have f of z, you know, f of z is 1 over z, and you already know what z is, right? That's z is x plus iy. So you may want to do whatever with this. You may want to simplify this function somehow. You say f of z equals, I know the way to simplify a function like this is to multiply the denominator by its conjugate, x minus iy. And of course, f of z in that case will just become x minus iy all over. Of course, you already know this is going to give you x squared plus y squared. Like we know, it's going to give you x squared plus y squared. So you can see that f of z is more like x over x squared plus y squared minus I y over x squared plus y squared. So that kind of a thing. So this one takes x plus iy for z, and then it outputs another complex number like this. So that's exactly the idea we are trying to talk about when we talk about complex functions. Okay. All right. So complex functions can be visualized by graphing their real and imaginary parts separately. We already saw how we were graphing complex numbers the other time, right? So you make something like the Cartesian coordinate system. What should have been your x axis becomes the real axis, and what used to be y axis is now the imaginary part. And then if you have something like 2 minus I, for instance, that is 2 that is 2 on the x-axis here, and minus 1, minus 1 on the negative on the other part. And then that the point we talk about is something around here. Sorry for that overlap. So, and then you draw this from the origin. So that is so this point is 2 minus I, like that. So that's a kind of thing, right? But when it comes to complex functions, right, things get more complicated. So you actually need to visualize these things using some more powerful ways, as we're going to see very soon. So contour plots can also be used to visualize complex functions where curves of constant, real or imaginary parts are plotted. Okay. And then computer software like MATLAB or Python libraries such as Matplotlib can be used for accurate graphing of complex functions. So I use Python a lot, so you're going to see plots or graphs made with matplotlib in Python, right? That's what I'm using. I remember I used MATLAB back in the days when I was doing my bachelor's and master's degree in Nigeria. But I mean, in the last 1.5 to 2 years, I've been focusing a lot on Python. Okay, so let's talk about types of functions now, types of complex functions, just like we had in for complex functions of real variables, right? I mean, the functions are pretty much the same, except that in this case now, these functions are taking complex variables. So look at this function now, f of z equals z squared plus 2z plus 1, right? So if you look at, so this is simply a polynomial function. So in that case now, it's like you have f of z, which is equal to, so instead of z squared, now you have x plus iy squared, right? Plus 2 into x plus iy plus 1. So you can simplify this, right? So it has taken x plus iy, and then it's going to output something for you. If you square this, of course, you're going to get x squared plus I 2xy, right? Then plus, for this part, now you have 2x plus I 2y, 2 times x, 2x plus I 2y, then plus 1, right? So in that case, you can tidy things up already. You have f of z to be. So if you put all the things without I together, you have x squared plus 2x plus 1. That's a quadratic expression right there for you. Plus I into 2xy plus 2y. So that's what f of z ends up giving you, like that. So that's how that works. So you see here that polynomial functions are entire functions, meaning they are analytic everywhere in the complex plane. So in this case now, the idea of analytic functions and everything, you're going to come across them when I do. I think I'm still making videos on complex analysis. We still have, I mean, I shouldn't have less than five, or I mean, I should have between 5 and 10 videos to complete videos on complex functions. So you're going to talk about the idea of analytic functions, harmonic functions, and things like that. So, but generally speaking, one property of polynomial functions is that they are entire functions. That means that they are analytic everywhere in the complex plane. So you're going to understand the concept of being analytic. And when we introduce things like the Cauchy, uh, 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 there's a, I think, is it Cauchy function or something like that? I know there's something Cauchy. I think there's still something I'm forgetting, but when we get to that video, you see that. Then they also have finite poles and zeros. So that means that you can get all the solutions. That's what this means, right? So poles are, of course, zeros are uh when you equate the function to zero and you solve for z or something, you can get those values out. Then poles are points of discontinuity, as you're going to see later. And of course, when we go later also into the idea of poles and zeros, you get better clarity on this. Okay, so let's go to the sixth slide where we have more information on other types of functions, I believe. Okay, yeah, still talk. So now, since we've introduced the ideas of zeros and poles now, so I thought it's important to actually elaborate on that idea. So zeros of a complex function are the zeros are the points where the function equals zero. They represent solutions to equation f of z equals zero. So like if you're looking for the zeros of f of z that we just considered, which is z squared plus 2z plus 1 equals 0, right? So if you're looking for the zeros, it means you're solving this for z. So that means, and here, it's more like, can we factorize this? Okay, of course, if you cannot even factorize. I think factorization is possible. Yeah. So you have z squared plus z plus 1 equals 0. Then you can factorize z out here. So you have z into z plus 1. Okay, good. Z into z plus 1 plus 1 into z plus 1 equals 0. So simply, you have z plus 1 squared equals 0. So, the other time we're told that they have finite zeros. That means you can know all the solutions. So here now it simply means you have z equals minus 1 twice, z equals minus 1 twice. That simply means that, of course, if z is minus 1 twice, that simply means that you have x plus iy equals minus 1, something like that. Something like that. So, I mean, you can do whatever you still want to do with this, depending on the situation you find yourself in. So, So it means that this has finite zeros. That's two zeros. The zeros are the solutions of the function. Basically, that's what we are saying. All right. So, or the roots too, if you like. So poles, on the other hand, of a complex function are the points where the function becomes infinite or undefined. Now, in this case, this function is defined everywhere, but you have the case of infinite when you have a case like one over z. So in the case of 1 over z now, and it's at the point where z equals 0, this function will be undefined. So in that case, you can say that that this function f of z equals 1 over z has a pole at z equals 0. So we're going to dive deeper into this in videos after this, right? So they correspond to the points where the denominator of a rational function equals 0. So in the same way, if you have, say, f of z equals z plus 1 over z squared minus 1, right? So if to find the zeros of this function, you just equate z plus 1 equals 0. So the zero of the function is minus 1. On the other hand, if you're looking for, so this is 0 now. So to find the poles of the function, right, you equate the denominator, right, z squared minus 1, you equate that to 0. So here, you're going to get z minus 1 into z plus 1, and all of that equals 0. So that means you have 1 and minus 1 as the poles of this expression, like that. So it of course, maybe a better way to even, you can simplify this further, right? Um, and you can simplify this for that to be 1 over z plus 1. So, so it has no zero or something, and then the pole is at minus 1. So, I mean, that's the kind of approach you should have to that. So if you're looking for zeros, equate the numerator to 0. If you're looking for the poles, equate the denominator to 0. That is the kind of thing you do. I mean, you have something like that also happening when you talk about functions of real numbers, right? So if the just like what you call pole here are points of discontinuity for real numbers, points where the function is undefined, meaning that when you equate the denominator to 0, the values you get there at those points in real numbers, you call them discontinuities, but here you call them poles. Then the zeros you have here is also the same idea. So equate the numerator to 0, whatever you get, those are the solutions of the function when you solve them. So zeros for real numbers and real functions and complex functions, then discontinuity for real function, whereas you have poles for complex functions. Okay. Of course, this is a representation, this is graphical representation of this polynomial function, z squared plus 2z plus 1. This is this is what the graph looks like. I mean, so you see it like some kind of contour plots like that with some, you have some kind of discontinuities right in the, oh, should I call that discontinuity? I don't think that, because the function itself is continuous everywhere, right? So, but I mean, from the idea of contour, so it means that there's a lot of gap, in that particular center. Okay. So let's go to the next, talking about trigonometric functions. Trigonometric functions. So consider the function f of z equals sine z. Of course, this is simply the same thing as sine x plus iy. Well, I don't know. Of course, we can expand this, right, using laws of trig. Interestingly, I've not still done videos on trig up till now, but I mean, I have a lot of things coming in. I have a lot of requests from different places. So if you have something you want me to, a topic you'd like me to talk about too, I mean, feel free. So I'll just queue everything up and I'll take them in the order in which they come. So of course, you can use the idea of sine, the sum of sine sum here or something like that here. And then, this is going to be sine x cos iy plus cos x sine iy, something like that. So whatever you can do with that, you are free to do that. So that's for trigonometric function. So trigonometric functions are periodic with period 2 pi. So it means that after every 360 degrees, you come back to the same thing again. And of course, you have the sine curve, right? So it goes through the origin, it comes, goes. So this is like 180, this is another 180. So the periodicity means that it comes back to the same point after 360 degrees. If you start from here, so it goes 90, 90, 180, and then it comes back to the same point you started from. That's the idea of periodicity, right? So trigonometric functions are periodic with period 2 pi in the complex plane, and they have simple poles at points where their argument becomes singular, such as plus or minus I. So simple poles, you have sine z equals 0. For you to solve this, right? I mean, you have to, so you need to make your plot. At which points will sine z be 0? So you see sine z is 0, it's zero here, it's zero here, and it keeps going like that, you know. So that this is like 0 degrees, this is 180 degrees, this is 360 degrees. So you can already say that the poles are, say, oh, we are talking about poles here, poles where they're undefined. Well, I mean, for sine Z, it's like sine is defined everywhere. Yes, sine is defined everywhere. It's defined for every angle. It's not like tan. Tan is not defined for 90 degrees, for instance, so like that. Of course, this is how a trigonometric function, that sine Z, this is what it looks like when you plot it. So like I told you, I made this with matplotlib in Python. So this is the graphical representation of your sine Z. And then we talk about exponential functions, exponential functions. So in this case, we have f of z equals e raised power z. So f of z equals e raised power z. That's more like e raised power x plus iy, and that is equal to e raised power x times e raised power iy. Now, does this look familiar to you? This looks like the Euler formula, so you can actually write this as e raised power x into, so following the Euler formula, now you have this is cos y plus I sine y, that's how you break this down like that. So that is so cool. So that is what an exponential function looks like. So the properties of exponential functions are entire function with no zeros. That is, if you solve for this now, you won't get any value. It's just that. So it's entire, it means it's defined everywhere, but it has no zeros. And then they grow exponentially as the absolute value of z increases. So, e raised power x. So you have maybe some kind of growth going that way. So just exponential, just increasing so sharply. All right. So that goes. And then we continue to look at the graph of exponential function. Like you can see this graph of f of z equals e raised power z. This is what it looks like. So you have all the lines coming in that right-hand corner like that. Okay. So we talk about logarithmic functions next, logarithmic functions. So logarithmic function, consider the function f of z equals log z. You have f of z equals log z. That's like log x plus iy. What can we really do with this? Uh, Nothing much, I believe, because if it was log ixy, then you could split it up. But I mean, this is how it goes. So logarithm functions have branch cuts along the negative real axis. So along negative real axis, because the logs are not defined along negative axis or something like that, right? So you have branch cuts. Now you have the definition of branch cuts. You have that down here we are going to talk about in a moment. So they have multi-valued with different branches differing by integer multiples of 2 pi I, 2 pi I integer multiples. So talking about branch cuts, right? Branch cuts are discontinuities introduced to definite single-valued branches of multi-valued functions, such as logarithmic and square root functions. Now you remember that if you have if you have y equals roots z, for instance, so to speak, or normally let's even say y equals root 4, right? So for one value of y, say, okay, um, I'm trying to look for a very good way to explain this. So, okay, if you say y equals root x, let's just generalize it that way, right? So you see that for one value of x, if you say x is equal to 4, it's going to branch out. Y is going to be -2 and 2. So that's a kind of idea of what that branch cut thing is talking about. Okay, so branch cuts are discontinuities introduced to to define single valued branches of multi-valued functions, such as logarithmic and single root functions and square root functions rather. They are typically chosen along lines or curves where the function becomes multi-valued. So let's see the plot of that. Now you can see, so you just see all the lines radiating out all over the place like that. So you have the logarithmic function log z staring you in the face like that, like what you have right here. Okay. So talk about rational functions. I think I talked about this previously. So consider the function f of z equals 1 over z. So and then you have f of z, f of z is 1 over z. Now, I told you the other time you could actually say this is 1 over x plus iy, and you rationalize, you get x minus iy. And of course, if you multiply this by itself, it just simply gives you the absolute value, which is x squared plus y squared. And that's the same as x over x squared plus y squared minus y over x squared plus y squared, like that. So, like that. So, properties now, the rational functions have poles at points where the denominator becomes zero. All right, where the denominator becomes zero. When you put z to be zero, then there's a pole right there. And they have finite or infinite poles. They have finite or infinite poles, depending on what you're looking at, like that. So, um, and then this is what this looks like. Of course, because there are jumps, all this dotted line you see now, it happens around zero, like that. So, because there are definitely bound to be jumps in those places. So, yeah, let's move on. We have a few slides to reach the end of this. Okay, let's talk about rational functions, right? Of course, that 1 over z is a rational function, right? But in fact, it is more like an inverse function, so to speak. But it's technically a rational function. A rational function, like I told you, well, I don't know if you have seen my videos on basic calculus, right? When I was talking about functions of real variables, I said a rational function is a ratio of two polynomials. So like z squared plus 1 is a polynomial, all over z squared minus 1, that's another polynomial. So this is a rational function, right? So just like you have 1 over z, it's also a rational thing, because what you can technically see 1 as a polynomial. That's 1 x raised to power 0 all over z, right? So now this is the graph of f of z equals z squared plus 1 all over z squared minus 1. So obviously this one has two jumps. So it has two jumps here. Of course, yeah, if you have z squared minus 1 equals 0, so it means z is either 1 or minus 1, because z squared minus 1 is z into 1, z minus 1, z plus 1. So it has two poles at 1 and minus 1. And that's why you have those jumps happening right here. So around these two places, as you can see, you know. So you have jumps taking place around minus 1 and 1 as expected. So that goes. And then in conclusion, right, complex functions are powerful mathematical tools with diverse applications. Understanding their properties and graphing techniques is essential for various fields of study. And I will not leave you without giving you some things to try your hands on. So the first question here is to investigate the behavior of the function f of z equals e raised to minus z as z approaches infinity. And then 2, discuss the properties of the complex function f of z equals sin z. That's hyperbolic complex function, right? And its relation to the hyperbolic sine function. Then determine the poles and zeros of the function f of z equals z cubed minus 1 over z squared minus 4. So to get the poles, to get the poles, you equate z squared minus 4, which is the denominator, to 0. To get the zeros, you equate z cubed minus 1 to 0, basically. And then number 4, explain the concept of branch cuts in complex analysis using the function f of z equals root z, right? Equals root z. So, I mean, try your hands on this and see if you really understand the concept. Thank you very much for coming this far into this video. If you have not subscribed, be sure to do that. And don't forget to like, to share, to comment, and, make sure this circulates to as many people as will find this very helpful. Thank you for listening. See you in the next video.